Okay, so I'm going to take you through the process of actually doing LCA and step-by-step workshop here. And all this content is available on the venturewell.org/tools-for-design website. So start out there and you'll see this introduction page. This is a whole class on green design, but what we're interested in is life cycle assessment. So go to measuring sustainability and then life cycle assessment. So there's the main page just describing LCA with a PDF primer to read and various other info and links. But what we care about right now is the exercise. And this is going to step you through everything. We're not going to take 3 to 8 hours to do this right now. I'm going to give you a quick once over of this, and feel free to pause and rewind, replay whenever you need to during this video. It goes quite fast, and I'm assuming that you'll pause whenever you need to. But we'll start step by step. So step one, decide on your scope and boundaries, functional units. Now, every LCA needs a goal. We're all just going to decide that the goal here is to quickly estimate the priorities for eco-design. So we're not going to do a full-fledged detailed LCA. This is just a quick and dirty fast-track LCA so that we can decide on priorities for sustainable design. And then choosing your scope, what we will and won't consider. So we're going to do a refrigerator here. And that's going to include all the materials and manufacturing of the fridge, all the raw material extraction, and the transportation to get from the raw material and manufacturing to the user. And then it'll include the use phase, the electricity during life, and the disposal at end of life. But it's not going to include, let's say, the food that you put in the refrigerator or any other parts of that system. So it's going to be cradle to grave of the refrigerator itself, but not larger systems. And so then choosing the functional units so that we could make comparisons between other refrigerator designs. We could choose environmental impacts per hour of use. That would be a nice standard thing. But to make the math simpler on us, I think instead I'll choose environmental impacts per 15-year lifespan of the fridge with it operating 24 hours a day, 7 days a week. And just to make an additional comparison, or in case we wanted to compare this to smaller fridges, you might say, oh, we'll save energy by having a small fridge. We'll save materials by having a smaller fridge. That's fine. But just to make it a fair comparison, let's assume that I have a family and I'm storing food for several people, so I need like a cubic meter and a half of volume for storing food. So let's say my functional unit is environmental impacts per 15-year lifespan of the fridge holding a cubic meter and a half of food. And then next stage is listing your inventory. Now this is actually already done for us in this exercise because I have a downloadable PDF that you can use here. And this has all the materials and the quantities in both kilos and pounds, and the manufacturing methods. So steel is cold rolled, the iron is cast iron, the aluminum is extruded, etc. And it's got the transportation. Sorry, these are only in miles, not kilometers, but we can convert. And then lifetime usage, so it lasts for 15 years, that was our assumption, and it's used 24 hours a day, uses 70 watts of power on average, and so that works out to 613.2 kilowatt hours per year. And then at end of life, we'll choose landfill as the disposal. So that's it for your inventory. And obviously, if you're doing your own product, you'll have to assemble all that information. But this is just an exercise. We have it here for you. And then step 3, actually calculating your impacts and then figuring out your uncertainties or your scenarios for sensitivity analysis. And this is where you enter all the data. Now, you will not always know what materials to choose in the database, and the database will pretty much never have all the right materials that you want, so you're going to have to make some estimations. And sometimes you can deal with that by saying, I think it's these impacts plus or minus 50% or 100%. But sometimes you need to be a little more precise or a little more extreme and try out different scenarios of what if it's scenario A, what if it's scenario B, to test your assumptions and where you might be wrong. So you can either do this in LCA software, which is generally easier but less transparent. But since this is just a basic exercise, we're going to use this template here. So that will download. Okay, so that just downloaded there. All right, so here is the template spreadsheet. And over here on the left, we've got sections for the manufacturing stage of the life cycle, the transportation stage or stages, usage, and end of life. So all your materials and manufacturing methods go here, and all this stuff gets graphed here, and then there's another graph that agglomerates things so that rather than line item by line item, which is this graph, you'll see it by the total life cycle stage. So all materials and manufacturing gets wrapped up into this bar, all transport, all usage, etc. And you might notice that there are these weird blurs at the top of each bar. You can't quite tell where each bar begins and ends. That's because, especially when we're doing quick and dirty fast track LCA, we're making estimates. We're not having super precise data here. And so we need to account for uncertainty. And we've got different levels of uncertainty depending on how certain we are. So even if we were absolutely, completely certain about everything, that would still be plus or minus 10% uncertainty. But for some things that we don't know at all, we might say plus or minus 100%. We have no idea. Okay, and you could be even bigger, but the graph kind of breaks if you do higher. So again, this is just rough estimates. But so you've got different columns here for the eco-intensity. This is the environmental impact per kilo of material or material processing in the case of manufacturing. In the case of transportation, we'll get to this later, but it's eco-intensity per ton kilometer. That's per ton of material shipped for 1 kilometer in different modes. And then for usage, we're just looking at electricity use, so that will be environmental impacts per kilowatt hour. And then end of life, we're back to environmental impacts per kilo of material that's being disposed of. So that's the eco-intensity, and then how much of that material or other thing are you using? And then how many of those items do we have per functional unit? Remember that I said that the functional unit here is a 15-year lifespan of a refrigerator that holds about a cubic meter and a half of food. So the reason I did that was so that I just have one item per functional unit for basically everything. But your mileage may vary. You might have a different system that you are trying to analyze. And for example, if I had if I were comparing this to 2 small mini fridges, and together those 2 mini fridges had the same capacity as one full-size fridge, the original fridge, then all the materials in manufacturing would be doubled because I would need 2 mini fridges to be the same as one fridge. And then I would make this number 2 for everything. But that is not the case here, so I'm going to put it back to 1. Okay, so looking back at that bill of materials here, what do we have? So we have steel, we have 47.6 kilos of steel. Okay, so what is the eco-intensity of that? Well, in the database that I'm going to use here just for simplicity, I'm going to use the Ecolizer downloadable PDF. And actually, I'm not going to view this in a web browser because that's not super convenient. I'm just going to save it to my desktop. And then I can open it up in PDF viewer. And I call this a database, but yeah, it's really just a lookup table PDF. But you can still search it. And it has a table of contents here. You can see it has information on various different categories of stuff. So ferrous metals, non-ferrous metals, plastics, wood, paper, energy, transport, lighting, various other stuff, chemicals. And so the easiest way to find things in here is just to search. So I'm going to do a search for steel. Oops, steel. Okay, so this is in the table of contents, blah, blah. This is an example where they take you through how to do stuff. Okay, stainless steel, but it's actually not stainless steel. If we go back to this, it just says, it doesn't say stainless, it says primary steel, which means virgin steel, not recycled steel, but it's just normal low alloy steel. So let's keep looking here. Okay, so here is not stainless steel, but just normal low alloyed steel. And okay, so that has 231 millipoints per kilo. This is how this particular database or PDF measures environmental impacts. And if you go back to LCA main page or info page here, it talks about the recipe methodology for LCA and how it measures 18 different environmental impact categories that you see listed here, and then it combines them all into these units of points. So that is what these points are, but millipoints is 1/1000th of a point. So okay, 231 millipoints. Okay, so type in 231 there. You can see that I already had that in there because that was what I was doing last time. But anyway, but then, okay, how many kilos of material do we have here? Well, we have 47.6 kilos of material. Okay, so 47.6, boom. All right, and now what is the processing for that? Well, the manufacturing method, okay, cold rolled steel. Okay, so that is the manufacturing method. So if we look at processing methods for steel here, we have drilling, deep drawing, turning, and hot rolling. So the steel that it's talking about here is for the structural frame of the refrigerator, and so probably this is going to be the closest thing that we can find. But again, sensitivity analysis, like it told you in the exercise here, you're not going to be exactly sure what everything is, and find your best substitutions or proxies as you can, and we'll ideally run different scenarios to check your assumptions. So, okay, for now, let's say hot rolling. Okay, and so oh, right, so this was steel, and steel hot rolling. Or actually, we can say this is cold rolling in the bill of materials, but making note that substituted okay. So yes, that was 27. I had already typed that in earlier. But yes, 47.6 kilos of steel is what was used. Yeah, so 47.6 kilos of steel that was cold rolled. Okay, next one is iron, and there's 4.5 kilos of that. So, okay, I'm going to do a search for iron. Oh, that's a lot. Okay. Okay. And you can see the different categories are color coded. That's how I was able to skip ahead here. Okay, so here it says cast iron, 173 millipoints per kilo. Okay, so iron. And notice a kind of funky thing here. This has cast iron as all one thing. That means that it is both the material and the manufacturing process. There are other kinds of casting here that are additional, but as our baseline, we can take cast iron. So because on here, it says that the iron is cast. That is the manufacturing method. Okay, so cast iron, 173. And there were how many kilos of it? There were 4.5 kilos of it. Okay, and now we can make a note here, includes manufacturing method. Okay, so this will be something else. And then next one is aluminum, and again this is virgin aluminum, not recycled aluminum. Okay, there's 2.1 kilos of that, and it is extruded. Okay, so we'll do search for aluminum, although this uses the British spelling, so aluminium. Okay. Again, going through here, I'm just going to skip there. Okay, so aluminium. Okay, so impacts per kilo is 1045. Kind of a lot. And there were how many kilos of it? 2.1 kilos. Okay, and aluminum extrusion. So what are the impacts on that? Processing. Section bar extrusion. So that is 92 recipe millipoints per kilo. And again, there's 2.1 kilos. So, okay. And now you can see here in the graph that even though the environmental impacts per kilo of aluminum are huge, the total impacts are nowhere near as big as for steel, just because we're using a lot more steel. Oh, but actually we can pull this uncertainty down because we do know pretty much what this is. So steel, the material, yeah, we know exactly what that is. For cold rolling, that was not a perfect match with what we have in the database, so say 30%, but we'll give those the same. And yeah, we don't need notes on that or that because they just had it in the database as is. Okay, so aluminum extrusion, and we're not going to do the whole thing, but let's just do one more here to continue the example. Okay, so copper primary, 2.7 kilos of that, and the copper is drawn into wire. And that's because this is the wire that goes through the refrigerator, both for the coils of the motor and for other electrical wiring. Okay, so copper, look up here. Okay, so that has 774 recipe millipoints per kilo. And there were, how many kilos? There were 2.7 kilos. And copper wire drawing. And, right. And, okay, so processing wire drawing, 209. Okay, and okay, and you can see us building up the bill of materials here. And you can, obviously we need to add some more rows here, so we'll just insert some rows, we'll do that multiple times, and then we can add more stuff. Now, just a note, this graph here is generated not directly by the stuff over here, it's actually being generated by columns over here. And so to keep these going, you just copy and paste down so that they keep going. And so now if you type in more stuff, you'll see that it populates in the graph. And you know, if I add in more things here, then you'll see those things appear in the graph as well. Also need to copy and paste this all the way down to keep it going. Okay. So, so that's how you can expand this table to include more stuff. But just in the interest of time, I'm gonna leave the rest to you there. You know, keep going down the whole bill of materials here, and notice how it says at the end, other materials. Yeah, once again, I'm gonna leave that as an exercise to you to make an estimate of what else would be in there. And again, you will never have perfect info, and we're gonna want you to do some sensitivity analysis of plus or minus. And actually, these uncertainties that we're adding in here, that's a quick and dirty way to do these kinds of scenarios. When you say other materials, you know, there might be some electronics in there, and so maybe you'll say, I don't know, there's a printed circuit board, or yeah, so there's some kind of electronic component there, like a PCB. So a printed wiring board, surface mounted, the solder does not contain lead, so that's why it says PB free. And does it have, and yeah, surface mounted is probably better than through hole, because through hole is an older technology. And so let's just guess that there is, let's put this down in the middle here, printed wiring board for some kind of control electronics. And the eco-intensity of that is 22,345. but let's say, but how many kilos of it are there? There's probably just a few grams of it. So let's say 0.0, well, let's say 10 grams of it, okay? And there's one, and this is hugely unknown. We have no idea, so I'm going to attach an uncertainty of 100% to that. And so you can see we got the calculation here, and it's showing up there. So even though we really have no idea, you know, the uncertainty of 100%, we don't really need more info because it's a small percentage of the total impacts here. It's a very small impact compared to the amount of impact from steel. So, so that is a way to keep going through and making estimates. But what about the rest of the life cycle? So what's next in our chart here? Okay, we have transportation, and this is already pre-filled because it's kind of a standard thing. Let's assume that it is, well, in this case, it's ocean freight, and it's going 6,000 miles, and do a quick Google search of what is 6,000 miles in kilometers. Okay, so that's, well, let's say 10,000 kilometers. So what I've got here is a little formula saying that it's adding up all the stuff from materials and manufacturing and then dividing it by 2. So why is it doing that? It's because it's assuming that everything is going to be entered twice, like steel and the processing for steel. You know, that's the mass twice. But that's not always true because cast iron was only entered once. And so let's instead say, let's clean this up and say, actually, it is just the sum of this and this and this and this and this, and obviously anything else that you have in there, but you get the idea. And then what else is going on here? So it's dividing by 1,000. That's because we're converting from kilograms to metric tons, okay? And then times 10,000, so that was the number of kilometers. If I wanted to make that more precise, I could say 9656. Okay, so that's the amount of ocean-going freighter. Okay. That was in the bill of materials. Okay, and now looking up the intensity here. Okay, don't have that. Okay, shipping, transport. So barge, tanker, this would be for fluids like oil. And so transoceanic freight shipping. Okay, so that is 1.3 recipe millipoints per ton kilometer. Okay, and I already had that in here, so 1.3 millipoints per ton kilometer. And again, there's 1 per functional unit. And the uncertainty, I mean, we were told that, so we can say that it's well known. But transportation, you can often just take a wild guess, and it won't matter a whole lot because, as you can see here, transportation is already not that big an impact compared to materials and manufacturing, and we only entered whatever, 1/3 of the bill of materials so far. So, so it's often okay for you to have huge uncertainties for transportation. So, okay, so it went by ocean-going freighter for part of the time, and then it went by by rail for 500 miles. Okay, so let's insert a row for rail. And again, we're going to need to copy these formula cells so that the graph works properly. Okay, so rail, what's the intensity on that? Okay, freight train per ton kilometer, 3.9 millipoints. Okay, so 3.9. And what is the mass? So we can copy most of this formula, just not the distance at the end. Okay, and then the distance was, what was it? It was 500 miles, which is 800 kilometers. Okay, so times 800, and there is one of those, and let's say we're very certain. Okay, and so there we go, there's the rail impacts, and then truck. Okay, there are 50 miles by truck, and 50 miles is 80 kilometers. So let's see here. So again, we can copy and paste most of this formula. And we'll just multiply it by 80. Okay, and what are the impacts per ton kilometer? So the British word for a truck is lorry. So, and let's say that it's a big truck. It's a 32-ton truck, not a 16-ton truck. So the impacts per ton kilometer are 12. And so put that in here. And again, notice that even though the impacts per ton kilometer for trucking are way bigger than they are for freighter, it doesn't matter because it's such a short distance. Okay, so that is all the transportation, and you can see how small a factor transport is compared to materials in manufacturing, even before we have the whole bill of materials. And then electricity use. So let's look at, well, how much electricity use do we have? So, okay, we have the lifetime is 15 years. We already knew that. 24 hours a day use, 70 watts of power on average. And so the amount of energy per year is 613.2 kilowatt hours per year. Well, if it's a 15-year lifespan, then the total energy for its whole life is going to be 613.2 times 15. Oops, sorry, make that a formula. Okay, so there we go. And uncertainty, once again, we think that we know that exactly. Although let's go ahead and put some, and just leave this amount of uncertainty in here, because the amount of electricity that a fridge will use, it depends on how often you use it, how often you're opening and closing the door, and what you're putting in it, etc. So let's go ahead and leave that for now. That's fine. Or maybe let's say 20%, just again as a rough guess. So, okay, so what is the eco-intensity? Okay, electricity. And yeah. And so electricity, we don't want high voltage 24,000 volt. We want low voltage less than 1,000 volts. So this is the 240 volts that you get in Europe, or the 120 volts that you get in the US. And Note that we've got good electricity numbers for most European countries, but electricity in the USA, I added in on this PDF just as a separate comment. But we're going to say that we're in the Netherlands here, and so the impacts per kilowatt hour are 64. Okay, so that's 64, and so boom, so here are impacts now. Oh look, that is so big that all of the manufacturing stages just disappeared, basically. This is another reason why it's okay to do quick and dirty LCAs with high levels of uncertainty. Sometimes you just have one thing that dominates the whole life cycle. And if this were a refrigerator in the US, then it would be even more so. So between 81 and 93, depending on what part of the US you're in, like the South uses more coal power, the West Coast uses more hydroelectric. But if we changed this to 93, then wow, really everything else just disappears and is totally irrelevant. But just for the sake of thoroughness, for finishing up here, we've still got end of life to do. And so end of life of material A was steel, and material B was iron, and then there was the end of life of aluminum. And so let's look at what those are. So if we go back to the pages for steel, okay, steel, you see there's the production, the processing, but then at the bottom there is potential recycling or waste treatment if it's just getting thrown away or burned. So here we were assuming that the disposal is landfill, not recycling, and so we're just going to do this waste treatment. So that is 26, and that was already typed in there, but whatever. But the mass, that is that amount there, so 47.6, and again, one item per functional unit. And we can leave the uncertainty high. It really doesn't matter. Even if I cut this out for a second and just look at the manufacturing versus end of life, that end of life still doesn't matter compared to the initial material extraction. And so we'll put that electricity back. And okay, and then end of life of iron. So look up iron. Okay, waste treatment, again 26. And the mass of the item was 4.5. And okay, and then aluminum or aluminium as it says. Processing, okay, waste treatment, again 26. And also notice this exclamation point. That is telling you that that is very uncertain data. So it's actually good to keep a high uncertainty when you've got something with an exclamation mark there. So we can even say like 50% for iron and aluminum. But okay, sorry. Yeah, so that was the same impact, and then the mass was 2.1. Okay, and etc. You get the idea here. And again, all these things are so small that they don't really matter. That doesn't mean that designing for end of life doesn't matter. It just means that if you design for recycling, the improvements that you're going to get are by lowering the materials and manufacturing impacts of the next round. So it's not that the end of life is where the big impacts are, but designing for circular economy also fixes the materials and manufacturing. So that is the basic gist here, and obviously you can keep going through the whole bill of materials, get all the materials and manufacturing methods in there, and we've got these big uncertainties here, so that can be totally fine for you to deal with what it was saying here, of dealing with your where your assumptions might be wrong and your sensitivity analysis. And so what we've done here is we've calculated all the stuff, and so now we need to interpret the results. So one thing that we might do in part of our interpretation is we might say, there's still too much uncertainty in some things. Let me just run a whole separate scenario so I can make a copy of this whole thing, okay, and I can, let's say, scenario 2, let's call it. Okay, so maybe this first one was scenario 1, and now I've got scenario 2. And so maybe in scenario 2, I have a solar-powered fridge. And so I look back, electricity. Okay, and okay, so electricity according to different sources. So I could look at a fridge that's entirely nuclear powered, if you have your own home nuclear power plant. Gonna skip that one. So solar energy and various different kinds. Let's say that it's single crystal silicone solar panels on a flat roof. Okay, and so that changes this number to 7, and I can make a note that it was flat roof, single crystal and silicon. Okay, and now you can see that the use phase, it still dominates, but it's not like an order of magnitude or two bigger than the materials in manufacturing like it was before. And so maybe if I entered in more of the bill of materials here, they might be more even. Or if I had a walk-in fridge that is very energy efficient because the surface area to volume ratio is better, but it uses more material, maybe it uses 100 kilos of steel, then, maybe all these things get bigger, or whatever. Anyway, you can do an entirely separate scenario here that has all kinds of different stuff. It's different materials, it can have different transportation. What if we double the transportation here? And you can see if it makes any difference. Now, in this case, even these extreme measures are not making much difference. And so it's still energy use that's the dominant impact. And so this is part of what the interpretation is. What has the biggest impacts, and what impacts change the most with different assumptions. So here, the electricity use, if we switched from normal grid power to solar power, that made an enormous difference, far more than even doubling the amount of steel, which is kind of a ridiculous thing unless it's a giant walk-in fridge. And so that's what the system was most sensitive to. And Sometimes interpreting these graphs may make you choose different boundaries or different functional units. That's fine. Just go back and redo the analysis. And so the bottom line here is, what are your priorities for eco-design? Based on what were the biggest impacts here, what is your top priority to design a better refrigerator? So even if we're switching from a grid electricity version of the fridge, where electricity is the only thing that matters in the entire life cycle of the product, to a solar-powered fridge, where electricity use is still the biggest impact, but not the only significant impact, it doesn't matter. Either way, our priorities for eco-design are to design a more energy-efficient fridge. So that tells us where you should focus your creative efforts. And then the last part of the exercise is just a checklist for self-assessment. So you can go through, did you do this? Did you do that? Et cetera, et cetera. So when you write this up, you're going to want to write down how you did all these things. You can write this up nicely in a Word doc and paste in the graphs and the table for all the data, so that you can be very transparent about the assumptions that you made, particularly the notes that you made on when you were substituting or changing things. Okay, so that is basically it. I know that this was a lot, but as you can see, even though the whole process of LCA is pretty complicated, each individual step is quite straightforward. And I hope that also this way of handling uncertainty and looking at best case, worst case scenarios will also reassure you that you don't need to have all the data and perfect knowledge of everything in order to make intelligent decisions. So this is basically it for quick fast track LCA, and good luck using this as a tool for making better sustainable design decisions.